There we go. Okay, how is the project number 1 going? Did anybody start yet? Did anybody finish yet?
Started.
What's that?
Started.
Started, okay, that's good. When I was looking at the previous lecture, oh, by the way, I was gonna ask you, I guess, do you prefer the homework and the lectures be at about the same time? Or would it be better if the lectures first covered the topic and then the homework was after that? I was wondering what synchronization makes more sense. After it? Yeah, I was thinking that probably makes more sense. The weird thing is that then we are discussing something else in the lecture while you are working on something different, but I guess you have it recorded, so you can always go back. You can't really go forward. You actually can go forward a little bit because there is last year's recordings, which are mostly similar. Okay, so what I wanted to do today, when I was watching the last lecture, I wasn't happy how I glossed over some of the concepts like affine space. I think I need to do a little bit more justice of explaining that to also help you understand the difference between points and vectors. I've been sort of assuming it's intuitively understood, but there is actually pretty nice theory behind it, or nice formalism, nice mathematics behind it, and I think it's good to formalize these things a little bit. So let's start by, it's going to be mostly me writing. So the differences between affine versus vector spaces. So let's, before I will get to the formal definition of an affine space in a little bit. Oh, sorry, I need to make it bigger. Just yell at me. There is something wrong on the screen. And I can also hide this. Did it work? Do you want me to rid of this one? Is that better? Or was it better like this? Who votes for this one? What? This is good? All right, because now we have some sunlight from the outside. Okay, so I will give you the definition of affine space in a little bit, but let's first sort of talk about it. So starting with what are the elements of affine spaces. So in affine spaces, we talk about points. As opposed to vector spaces, we have vectors, right? So you should know almost everything about vectors. We had the formal definition and all that. But what I would like to clarify today, what exactly are these points, right? We had this homogeneous model and so on, but that provides only one part of the picture. So really the main deal is that in affine space, all elements, all points are equal. There is no special point. As opposed to in vector spaces, you have the origin. There is always, if I have a vector space V, there is always the origin, the 0 vector, right, which is a vector basically with all zeros. And it plays a special role there, right? That's the origin of a vector space. For example, that linear transformations we'll get there in vector spaces preserve the origin, always map 0 to 0. That's what we discussed last time, right? And the point of that's really the main idea, that's why affine spaces were invented. In affine spaces, all points are equal. All points are equal. There is no special point. No 0, which would have the special property that added to everything gives you does really nothing. If we measure coordinates in vector spaces, we measure them with respect to a basis, right? We discussed that. So let me just write it down. Coordinates, just to contrast, measured with respect to a basis. And what are coordinates measured with respect to in affine spaces? I sort of alluded to it the last time, but in affine spaces, coordinates or chords are measured in coordinate systems or frames. Those are just the same names for, so sorry, those are different names for the same object. Okay, And I will give you later today some specific examples. How do we do, what is the exact difference between coordinate transformations in linear spaces versus affine spaces? I want to walk through it in a little more detail, because also when you will be coding, it's very easy to make mistakes there. And the theory there is your friend, because that really tells you what is right as opposed to what might be boxed in your code, right? So important concept, so in vector spaces, we have linear transformations, right? We talked about them a lot. So what are some examples of linear transformations? Rotation, scale, and shear. I don't know, did I talk about shear the last time? How looks like a matrix of a shear transformation? Those of you who done graphics, you know it, right? Okay, I think I skipped that because I was trying to cover everything with the first lecture so we can start doing our homework, but then it came out a little more rushed than I was hoping for. So let's see, if we are in 2D, then for example, this would be an example of non-uniform scaling, right? That would be a scaling transformation. That would be example of a scale. Scale in x-axis by a factor of 2, scale in y-axis by a factor of 1, so no scale in the y-axis, right? So in general, it will be the alpha and beta. And if you do shear, so shear transformation can look like this. That could be like 1, 1, 0, 1, has some off-diagonal terms. And what it can do, if you have some undeformed object, what the shear will do for you is something like this. The easiest thing to understand this is to play with it in MATLAB, or to create like a little script that draws some simple object like this house or something, and then applies different matrices to it. So a specific example, like a numerical example, I guess, of linear transformation from 2D to 2D could be like this, right? Just whatever numbers I can think about, and or written using matrix vector multiplication like this, right? The reason I'm writing it here because I want to contrast it to what we have, the analog of a linear transformation in affine spaces. You have a question?
Yeah. In vector space, coordinates measured, then what's written?
With respect to a basis.
Oh, with respect to basis. Okay.
So the WRT, I meant with respect to the basis. Yeah.
And under scale, it's shear?
Shear, yes. Okay. You know what, I'll try to, I don't know, if I can sit, my handwriting will be better, but then I will see you worse. So it's difficult. So, any other questions? So the counterpart of linear transformations in affine spaces are affine transformations. Okay, and what is an affine transformation? A affine transformation essentially is a linear transformation plus translation. Or, okay, let me make it proper. So, transformation plus translation. So an example, if I was going to extend this to an affine transformation, by the way, would be perfectly fine example of an affine transformation too. But if I want to give more interesting example of an affine transformation, I could say that this, let me use the same numbers plus 2. I'm just inventing whatever numbers. The numbers don't matter. What matters there is that you have these two extra terms, the constants, both on x and y. So in both cases, the f is a mapping from R2 to R2 from like 2D, in this case it's 2D affine space to 2D affine space. The point is that it always takes 2 parameters and it returns two parameters. But here, the affine function has this extra part here. That's the constant translation. And if it's 2D, it has 2 components, x and y, right? So in general, we discussed last time the affine, the homogeneous coordinates. So in homogeneous coordinates, we can write this using matrix vector multiplication like this. So minus 2, 7, and minus 1. I guess this was minus, right? 0, 0, 1. And to multiply it by x, y, 1, right? And this last column here, that's just the homogeneous coordinates trick, right? So this 1 basically does, it adds this 2 and minus 1, so I can write it as matrix vector multiplication. That's what we talked about, right? Everybody happy about this? I just wanted to contrast the difference between vector space and affine space. And let me give you a proper formal definition of an affine space. You could still be like asking, what exactly is affine space, right? In vector spaces, I defined it properly, right? Remember, I said that a vector space is a set so first of all, vector space over the real numbers. So we'll be talking about both affine and vector spaces over reals over R. It's a set with certain operations, with the scalar multiplication and vector addition, that has to satisfy this laundry list of properties. It's like 10 properties, right? So let's take a look at how can we mathematically define the affine space. I think it's good to have a definition. So now you sort of already have an idea of what it is, and now let me see if I can explain how it's formally defined. I think the focus could go a little bit better. Let's see. Yeah, that's better, right? Cool. So the idea of the definition is essentially trying to forget the origin of the vector space. So affine and vector spaces, they are sort of similar. The main difference is that in a affine space, you don't have any special point. You don't really have any origin. Or if I reverse it, any point can play the role of the origin when I start talking about coordinate systems. So let's see how we can formalize this idea mathematically. So let me denote by A some set of points. So that's the set of points the affine space contains. And V is going to be a vector space, again over R, over the reals. And the final thing I need for the definition is a function f, which consumes pairs of points and produces a vector. Okay, and the function has to have these properties. So the function is such that first, for each x, y, for any 3 points, x, y, z, it is true that, let me get this right, fxy plus fyz equals fxz. And for every point, a function defined like this, fpx, which is a function going from points to the vector space V. It's defined, basically fpx means that I just fix the first parameter of the function. So fpx is like a parameterized function, which basically means I'm fixing the value of p. And then the second property says that this function is one-to-one mapping, bijection. Does everybody know what is a bijective function? What is one-to-one mapping? So somebody doesn't. Okay, so let me say that very quickly. So function in general is a mapping from one set to another set, okay? And there are 2 basic properties of functions. The function is called injective if it cannot happen that the function would map 2 points onto the same point. Okay, if I have fx equals fy, that implies x equals y, that means injective. The function is called injective. That means also that I can invert the function. Now, so that's one, that's injectivity, and then there is surjectivity. I hope it's taught in English in the same words, or onto or something like this. Surjective means that for every point here, I can find a point here such that the function maps there some value. And a bijection means that the function is both injective and surjective. So what it means, I guess, more intuitively, it basically means that if I have a function which is a bijection between two sets, that it means that I have elements of these sets, and the function gives me one-to-one mapping between the sets. Okay? So for every element here in the source, I can find exactly one in the image, such that the function maps the source to the image, and the other way around. So I can also invert the function and go from the target to the source. So I'm curious, who of you had a definition of bijective function before? Who heard it before? Okay, most of you did. Okay. I guess it can't hurt to repeat. So basically, what is it? So let me try to explain what is this definition. I guess it's not completely intuitive at the first reading of the definition, right? So, but after you give it some thought, it will make sense. So the affine space, I guess if you wanted to be super formal, you would say that affine space is a triple of A, V, and F, where A is the set of points. That's our working set. That's what we are working. V is the vector space, which is closely related to the points. That's really the idea of affine space, that it explains exactly how the points relate to vectors, which is exactly why I guess I wanted to formalize on that, to give you a clear picture of how points relate to vectors and how can we combine points and vectors and so on. We'll get there. So working on the definition, so we have this vector space, which is related to the set of points, to the affine space A. And what this function does, it takes a pair of points and produces a vector. Okay. Once we are in vectors, you already know how to deal with vectors, right? Because we discussed a lot about vector spaces. So this fxy that produces us a vector, so this equality is a vector equality, right? It means that this one vector plus another vector gives us this third vector. So what does number one mean? If I plot it graphically, if I have 3 points, if I have the point here x, y, and z, and if I draw the vector, if I imagine that the function f, x, and y gives me the arrow, the vector going from x to y, then it says this, that it says that the vector corresponding to x and y plus, I know how to add vectors, right? So this plus, if you think about the types, this plus is vector addition. Oh, now we have some nice contrast there. That's good. So plus this vector from y to z. And it says that this must be equal to the vector going from x to z. Okay. So this basically says, if I am to interpret it, this says that vector addition, this plus here, again, if you're programming it, you would know what are the types, right? So in this case, the type that would be standard vector space plus. And this number one property says that the function f, which assigns vectors to pairs of points, is in a sense compatible with the plus operation on the vector space. Or in other words, the vectors I'm producing, they sum as you would expect from vectors, or that the vector which I get from points x to z is the same as if I go through some middle point y. Okay, so that's number one. And what says number two? That's basically formalizing the thing I said before. Informally, it says that if I take any point there, I can basically identify the origin of the vector space. Because if I take this function and say that P is now some special point I'm for some reason interested in, I put there some coordinate system or something, then this function gives me a bijection between A, or one-to-one mapping between A and AB. And this one-to-one mapping is centered at P. And the P can be an arbitrary point. You see what I'm saying here? An arbitrary point, I can basically, if you want to, again, explain more intuitively, I can take the vector space and center it anywhere on the affine space. Okay? That will be obvious when we will talk about the coordinate systems and how we measure coordinates in affine spaces, which is really the main point. Why do we bother with affine spaces? Okay?
So you said you can basically put the center anywhere else?
So in an affine space, a set of points, you can say that So I guess if you imagine that this plane is my set A, 2D affine space, right? You can also have affine spaces of any dimension, right? By the way, this vector space can have an arbitrary dimension. The affine space will have the same dimension. I'm not going to formalize that because that would be too much. So what you were asking about is I can place my coordinate system basically anywhere. I can say that this point, P, A, or whatever, is the origin of my vector space. I can put it here. I can put it anywhere. And this basically says that any choice of this origin is equally good. Okay? Because I can basically measure vectors from any point. That's really what this f is doing, right? It takes pairs of points and gives me a vector. So if I fix one of the points, in this case I fix the first one, this p, right? Then this basically assigns a vector to every other point, and this says that this must be a one-to-one mapping. So there's a perfect correspondence between the center vector space and the affine space. Okay? I think I already explained every hair on this definition. Let's try to prove some very simple statements from this definition. So by the way, some simple types of proofs like this, they could happen at the midterm or the final thing. Very simple proofs. The first simple fact to prove, actually I would like you to prove using this definition, just to do a little bit of logical reasoning. So I claim that for every point, it's true that fxx is zero vector. Why do you think that would be true based on this definition? Yep.
The distance from a vector to itself is 0.
Sorry, say it again?
The distance from a vector to itself is 0, effectively.
The distance from a vector to itself is 0.
Look at the geometric interpretation of it, you have an arrow going from x directly to itself, which is the distance of it.
Correct. That's the right idea. Basically, if this picture collapses to the same point, right? So if I'm gonna formalize it, I can basically say that I use the property number 1 for all where x, y, and z will be all x, right? I can do that, right? This is true for any x, y, and z. So nothing prevents me from putting there just x, right? That I just say that y happens to be x. And z also, it will be x. Why not, right? That does not prevent me from doing that. Which means that 2fxx must be fxx, right? But these guys are vectors, right? So I can subtract them, which means that fxx must be a 0 vector, right? Trivial thing. It's equally simple to prove that fxy equals minus fyx. We can prove it in a very similar way. Does somebody want to say it? So I claim that I guess I should write for every x and y from A, it is true that this is my second toy proof, I guess. Yeah.
Well, if you do fxy plus fy
Yeah.
x, then that equals fxx.
Exactly. And from the previous, that's 0, right? That's exactly right. So let me write it down. So the idea is that fxy plus fyx must be fxx. And what we have shown here, that is a 0 vector, right? This is a vector, so I can subtract it, and I have this. All right? So by the way, by convention, usually we don't write this f. The f symbol is sort of arbitrary anyway. So often people just say that instead of, or let's introduce a convention, then instead of f of xy, we will just say y minus x. So basically you can interpret as defining subtraction on points, which returns a vector, which is really, that's what the idea of the function f is. And this sort of gives you the picture, right? Actually, it even makes sense if I plug the subtraction here to the defining property number 1, I get y minus x, that's here, fxy, right? Plus z minus y, and that gives me what? That gives me z minus x. So it works if you like imagine this y's cancel out by the subtraction. So it's a reasonable thing. So here is how vectors and points interact. And if you recall the homogeneous coordinates, if you recall our homogeneous coordinates, it all beautifully clicks in. So let's explain that. Okay, so let's bring homogeneous coordinates to the picture. So let me review real quickly that we said that x, y, and 1, if we are in 2D, that basically represents points in 2D affine space. Right? And if I want to represent vectors in 2D affine space, I do what? I do x, y, and what? 0. These things represent vectors. 2D. Okay. Technically, vectors are not elements of the affine space, but these things basically are compatible in certain sense, which I would like to elaborate on right now. Okay. The other way you can look at it from the projective, if you recall the projective plane idea, you can look at vectors as points at infinity. If the points are going further and further away, in the limit they become vectors. But here I would like to talk about combining about the operations we can do together with points and vectors. Okay. So the first thing, of course, you know that we can add vectors together, right? We don't need any affine space, right? I can do vector plus vector is another vector, right? So for example, x1, y1, 0 plus, and here my point is that the homogeneous coordinates representation is compatible with these rules. Because if I add the homogeneous representation of two vectors, I add these zeros, so I can get a 0, so I can get a valid vector. So I guess this is how you detect if it's a point or 0, right? If there is 1, it's a point. If there is 0, it's a vector. Okay. So here is the more interesting thing. You can do vector plus point, or equivalently point plus vector, and that gives me what? There are two possibilities: vector or point, right? Yeah.
Point.
Yes, exactly. Because 0 plus 1 is 1, right? So if I write it in coordinates x1, y1, so this is my vector. And if this guy is a point, so that it has 1 here, if I just add it per coordinate, I get 1 here, so that's a point, right? Same way if I did point plus vector, doesn't matter because this is commutative, right? It would still be a point, right? I guess geometrically you can look at vector addition as adding these arrows together, right? That's what we had in some previous class. And if you are adding, if you have a point, like represented by a little dot, and you add a vector to it, you get a point somewhere else. That's how you can look at it. Now another thing we can do point minus point. That's basically what was the defining function of a affine space about, right? And that gives me a vector. Because if I do x1, y1, 1 minus x2, y2, 1, I get x1 minus x2, y1 minus y2, and 0 here, right? So the idea is if I have 2 points, I can subtract them to get the vector between them. Or the vector pointing from one point to another, right? If this was my point P1, point P2, this would be the vector. The nice thing is that, again, that the zeros subtract, the ones subtract to 0, so everything nicely works with the homogeneous coordinate, which I think is sort of cute. Now here is a slightly more interesting case. What about point plus point? What is that? What do you think? It's a slightly tricky question, right? Because you can clearly you know that 1 plus 1 is 2, right? So what would that mean? The thing is that doesn't really mean anything. This is in general undefined. Now there is one special case where it actually is defined, and the special case is if I take two scalars alpha beta, such that alpha plus beta is 1, then I can do this, x1 y1 1 plus beta x2 y2 1, because that gives me obviously alpha x1 plus beta x2, alpha y1 plus beta y2, and then here I get alpha plus beta, but I assume that alpha plus beta is 1, so this is a well-defined point. All right. And by the way, this all, I'm just using the 2D example, but if there was a million coordinates, the idea would be exactly the same. That doesn't matter, right? Just it's more convenient for me to write it in 2 dimensions. So what is this? This special case where point plus point is defined in case I multiply the homogeneous vectors by scalars that sum to 1. So first of all, what is the geometric interpretation of this? If I have 2 points, as I usually do, 2 points here. For example, if alpha and beta is 1/2, both alpha and beta are 1/2. What is this geometrically? Yes, exactly, the midpoint, the point in the middle of the line segment joining. So if this was my P1, this was my P2, so it would be my P blend, if you will. Okay. And if I vary the alpha between 0 and 1, then beta, of course, also varies between 0 and 1, right? Because beta really must be 1 minus alpha, right? Then I basically trace this line segment from P1 to P2, okay? By the way, nothing prevents me from taking negative alpha. There's no problem taking alpha equal -1 and beta equal 2. No problem. What do I get in that case? If I have, again, P1 here, P2 here, what do I get if I take alpha -1 and beta 2? No longer the midpoint, right? But I think it's gonna be a point. I mean, it's gonna be a point on this line, right? I think it's gonna be the point here, right? Because it goes like 2. So in general, these things have names. This combination in general, this alpha 1 point plus beta another point, such that alpha and beta sum to 1. And that would also work if you were combining more than 2 points. You could be combining, okay, let me write it down. You could have P1 to Pn, and you could have weights W1, Wn, scalars, such that the sum of Wi is 1. So they form partition of unity. And then you can have valid point P blend, I guess, which would be Wi Pi. And it's a perfectly valid point because you think sum to 1, give me a point. So this in general is called a affine combination of the points. So let me write it down. Affine combination. A special case of affine combination is if all these weights are non-negative. In this case, that corresponds to alpha from 0 to 1. And in that case, we call it convex combination. All right. Have you heard this before? Convex combination, affine combination? Would it? So this should give you an idea that the sets of points are sort of nice. Now you can actually be thinking about, now you can differentiate between points and vectors. And in some cases it actually makes a difference, right? Because it makes sense to translate points around as opposed to vectors, which we usually consider free vectors. So it doesn't really matter where I draw the arrow. It's still the same vector, but on the points it does make a difference. Okay. So one more thing I need to explain before I can formalize a little bit the coordinate systems is the inverse matrix. I'll give you, I guess, a short introduction to the inverse matrix, because we will then do a proper introduction or proper definition and properties on how to compute it later on. But the idea of inverse matrix is no big deal. If I have a square matrix n by n, then we say that M inverse is also a square matrix n by n, such that, guess what, M inverse equals M inverse M equals the identity. Of course, the identity means n by n identity, right? So it means 1, zeros everywhere else, and that's an n by n matrix, of course. And this thing in between is, of course, matrix multiplication. I would imagine you have all heard about matrix inversion before, or did, right. So this is just how it's defined. Now the important thing is that not all matrices have an inversion, right? Think about this matrix, 1, 0, 0, 0. There's no way you can possibly invert this matrix. Why is that? Because if I have an arbitrary matrix A, B, C, D here, what is the product of the two? You should also be able to do product in your head. So this is 1, 0, AC, 1, 0, BD, 0, and 0. Okay, so there is no way to get here the 1, right? Because the last row times the last column gives me always 0. So no matter how I choose these ABCDs, I'll never be able to get their identity. So in this case, the inverse matrix does not exist. And we will have more to say about it later, because it has to do something with single matrices and rank of a matrix. And don't worry, we'll get there. Here I want to introduce the concept of inverse, so I can talk about the inversion of coordinate transformations, which is relevant to your current project. So let's see, for our basic coordinate transformations, the inverses are fortunately quite simple. So for example, for a matrix of translation in homogeneous coordinates, I think you might remember from the last lecture, if you were paying attention, what is the inverse? So the inverse must be some matrix such that when I multiply them together, I get a 3 by 3 identity. So who knows what is this matrix? What is the inverse of a translation in homogeneous coordinates? So if this would be matrix T, we're looking for T inverse.
Negative Tx.
That's right, yeah. So this is minus T, minus Ty, 0, 0, 1. And you should, I mean, we can easily verify that if we multiply the matrices together, we indeed get an identity, right? So try to multiply them. So the first row times the first column gives you 1. The first row times the second column gives you 0. The interesting thing is the first row and the last column, because it gives you minus Tx plus Tx equals 0, okay? And so on. You should be able to do this quickly in your head. Matrix multiplication might be useful. How about the inverse of a rotation? So if I have a rotation r theta, which is, again, if you remember from the last lecture, we discussed that it's cosine theta, sine theta, minus sine theta, and cosine theta when I assume it's the counterclockwise rotation, right? So do you know how it looks like the inverse matrix to it? I think that's also pretty simple. Aren't you falling asleep because you're getting dark? Well, I guess it can be either simple or tricky, right? So again, we are looking, so if this is my, let me write it like this. This is my r theta. I'm looking for some other 2 by 2 matrix here, the r theta inverse. such that I get the 2 by 2 identity, right? So what do you think is the inverse? Well, if you think about it geometrically, this is a counterclockwise rotation by angle theta, right? If I want to undo this transformation, what do I need to do? Rotate the other way around, right? Well, let's try that, right? So what does it mean, rotate the other way around? So that means that I do cosine of minus theta, sine minus theta, minus sine minus theta, and cosine of minus theta, right? But because of the properties of the trigonometric functions, cosine of minus theta is just cosine of theta, and sine of minus theta is minus sine theta. Oops, like this. So this would be the sine of theta, and this would be cosine of theta. Did I do it right? I think so. Yeah. So if you plug it in here, let's try that. If you plug it in here and if you carry out the matrix multiplication, you will find out that here I get cosine theta squared plus sine theta squared, which is 1. And here I will get cosine times sine and minus sine times cosine, so that's 0. And similar story here, sine cosine minus cosine sine, 0. Sine squared, cosine squared, 1. So indeed this definition holds. So I can say that the inverse of a rotation by angle theta is exactly the rotation by angle minus theta. Okay. And the last somewhat trivial example, what is the inverse of identity? That's easy. The identity, right? Because identity times identity is identity. It's good to see again that the matrix multiplication actually works. Okay, so now let's put the inverses to use and do the change of coordinates properly. I was just embarrassed how I did it before. I mean, it's good intuitively, but I prefer to do it properly. So let's do first change of coordinates in linear spaces or in vector spaces. I only glossed over it the last time, so let's work through an example. I think it's best illustrated on an example. So let's say I have one coordinate system. Sorry, in this case it's a basis, right? Here is the 0, which is my origin of the vector space. Now we are just dealing with vector spaces, so you can temporarily forget everything about affine spaces. And my first basis, let's say it has basis vectors called xa and ya. Okay? And let's say I have another basis. I told you that we can have several different bases, right? And the other basis will have a vector yb, and the xb is going to be identical as ya. So this thing here is one basis, this thing here is another basis. Okay, they are both perfectly valid bases because I can measure coordinates of any vector with respect to either one of them, and that's really the point of change of coordinates. So let's say I have some vector p here. Okay, and it's just one vector which exists in the vector space, but the vector will have different coordinates with respect to the basis a and with respect to the basis b. By the way, this is the best example I could think of, so that the things are not overlapping and not being crazy weird. So this is a vector p, and I can talk about its coordinates pa. So those will be the coordinates of the vector with respect to basis a. So the pa would be a two-dimensional vector of coordinates pax and pay. So what that means is, how do I do it graphically? I do the orthogonal projection of the vector on the coordinate axes. So what would be, in this example, what would be the numerical coordinates of vector p with respect to basis a, my vector pa? So I project on the x coordinate and on the y coordinate, and what do I get? Somebody dare to tell me the numbers? So I do orthogonal projection. I don't want to clutter the picture, so I just animate it here on X and on Y. And I'm talking about coordinates with respect to the A basis. So that's these two vectors. Do I hear -1, 1? That would be correct, right? Because if I project it here, I have to go -1 length in XA and +1 in YA. I get my vector P, right? So the same vector in coordinates with respect to basis B, let's call them PBX and PBY. What would that be? Exactly 1 and 1, because here now I'm projecting on these two vectors, right? So the projection looks the same, but now I'm measuring it in this direction as opposed to this direction. So this sign flips. Here I have to go +1 in YB and +1 in XB, and I will get my P with respect to basis B. So there are two ways how I can write my vector P. Okay, so one way is to say that it's PAX times XA plus PAY times YA. That's in one basis. I can write it using matrix vector multiplication more compactly as XA YA times PA. Okay. And in the second basis, I can write the same vector as PBX XB plus PBY YB, which again in matrix vector notation that would be XB YB and coordinates with respect to the basis B. Okay, so these guys are 2x2 matrices, because I'm doing a 2D example. Of course, in high dimensions that would work exactly the same way. It's just harder to draw. Okay, everybody got this? It's just about the notation, but the notation is important here to be organized. So because these things, here's the point, because this is the same vector just expressed in two different bases, then these two things must be equal, right? So I can write that XA, this is a matrix of the basis A, times PA is equal to XB YB times the vector PB, right? That's because this P is the left-hand sides are the same, so the right-hand sides have no other choice than being the same as well. Got it? And from this is obvious, and using the matrix inversion, that's why I had to introduce the matrix inversion. From here, it's clear how do I get the matrices corresponding to change of coordinates from one basis to another. So for example, if I want the matrix that changes coordinates from basis B to basis A, all I need to do is multiply from the left with the inverse of this matrix, of the XAYA matrix, and I get this. Watch this. XA, YA, inverse, XB, YB, and this stays the same, right? I guess I could put here a little identity, but you know that identity doesn't really do anything, so I don't have to have the identity there. And this thing here is exactly what we are looking for. Now we have sort of derived it as opposed to just sort of guessed it. So this is the matrix of change of coordinates from B to A. I think we were before denoting it as this, right? Like GAB. Take coordinates of a vector with respect to B basis and produces or returns coordinates of the same vector with respect to the basis A. Let's try in this example how it would look like. So in this particular example, I could write it like this. So this would be inverse. So XAYA, that's easy. Those are just standard basis vectors. So that's a little identity here. And the XA and Y, the XB and YB so the XB is what? XB is 0, 1. And YB is -1, 0, right? The inverse of the identity is just the identity. So the change of coordinates matrix is 0, -1, 1, 0. applied to PB. Yeah, sorry, I forgot the PB here. That was supposed to be a PB. Let's try it. Let's try it on this point P if it really works. So I said that the point P has coordinates with respect to PB, which are 1, 1. So let's try to plug it there. 0, minus 1, 1, 0 times 1, 1. And what do we get? We get minus 1, 1, which is correct. Those are the coordinates of the same point with respect to basis A. So indeed, this matrix performs the change of coordinates from basis B to basis A. Okay. By the way, what is this matrix? Does it have a... Can you name it? Don't name it just B or C. Tell me what it does. If you see it. I guess it's sort of, you can sort of guess it from this picture. Or you, yes, it's a rotation. In general, rotation looks like, let me again write it here, cosine sine minus sine cosine, right? So rotation about what angle? 90 degrees, that's exactly right. So this is a rotation about 90 degrees. It's just a temporary thing. So this, from this, it's obvious how the inverse matrix would look like. So by the way, I don't know if I have to write it. Well, let's do that. If I want to convert the other way around, then I multiply from the left with the inverse of XB YB matrix. So that gives me this. This gives me XB YB inverse XA YA PA. Wait a second. No. PB equals P. No. This was supposed to be PA. I'm sorry. This is PB. Yeah, sorry. This is PA. So that's if I want to go the other way around. I need to multiply this from the left by the inverse of XB YB. So I sort of get identity with PB, and I get a matrix which converts the other way around. This one was going from B to A, and this one will go from A to B. It turns out that this matrix, which I could call GBA, it turns out that the GBA matrix is exactly the inverse of GAB, that they are inverses of each other. Okay. Again, you could test it. You could again plug it in there and see it. I won't do that. I think I already explained that enough. Is it clear? Great. So let's try the same now in affine spaces. It will be just slightly different because of the translation. So change of coordinates in affine spaces. So let's try to do a similar picture. So in affine spaces, we have these coordinate systems which can be centered at any point of the affine space. So let's do the case where the coordinate systems differ just by translation. That's really the most interesting case because that's what the affine space can do, what the linear space can do, right? That's the translation. So I will have one coordinate system called A and another called B. They differ by translation T, so the directions of the coordinate axes are exactly the same. I will call them XB and YB. This I will call XA and YA, just like before, but now I also have the origins, okay? So if I have some point P somewhere, so mind you, now we are talking about points, and now we actually know what it means to be talking about points, right? So let's look at point P, and I can be looking at the point P from either frame of reference, right? I can be looking at the point P from the frame of reference B and the frame of reference A, right? So let's again do the same thing, and let's derive how exactly the change of coordinates from frame B to frame A works. So in the frame B, I can write my P as B, that's the origin, plus pbx xb plus pby yb, where the pbx and pby, just like before, those are the coordinates of my point in the frame B. So I can write it in a more compact notation as xb, yb, and here will be the pb. That's the vector which has components pbx and pby, just like before. The new thing here is that there is this origin B. Okay, notice that everything is cool. This is a vector, this is a vector, so vector plus vector is a vector, plus a point is a point, so all types match nicely. If you are crazy about like template metaprogramming and so on, you can like write like a library that will be checking the types for you. I heard some people actually did it and then hated it because then you have to actually worry about getting everything right. So how it looks like the P with respect to A? Well, it's a similar story, right? Now I start with A, and it will be PAX times XA plus PAY times YA. Written in matrix form, it's XA, YA, PA. All right. So now we are talking about the coordinates of a point with respect to coordinate system. So it's related to the previous idea, but not exactly the same, right? Because we have this origin here. But again, so what we will do now is analogous to what we did before. The left-hand sides, the p's are the same. So clearly the right-hand sides need to be the same too, right? So I can write that A plus XA, YA, PA must be the same as B plus XB, YB, and PB. All right, same train of thought as before. All right, and now what I want to do again is to relate these coordinates PA, so there's the coordinates of point P with respect to the A basis. I guess I could draw these vectors there. Oh, sorry, that was supposed to be straight line PA. And this is supposed to be straight line corresponding to my PB coordinates. So what I can do is this. I can move A to the other side. So here I will have B minus A plus XB, YB, PB. What is B minus A? It's a point minus point, so it's a vector, right? What vector is it? It's exactly this T. That's exactly the translation between the coordinate systems. So this is exactly my T vector, okay? And now I can again multiply it from the left by XA, YA inverse by inverting this entire matrix, and this will give me this. This will give me that PA equals XA, YA inverse times B minus A plus XA, YA inverse XB, YB, PB. All right, so this thing is a 2x2 matrix. That's, by the way, if you compare it to what we had before, that's exactly the same matrix as we had here. That's the change of coordinates in the associated linear space. So that's the linear part of the transformation. And this thing is a vector times matrix, right? Point minus point is a vector. Everything is cool. So this is 2x1 vector, right? So I guess let's go more concrete in this example. In this specific example, we know that PA is nothing but T plus PB, right? That's obvious from this diagram. And in this matrix form, we can write it as PAX, PAY, 1. So I'm just writing out the coordinates of the vector PA. And in matrix form, you can write it as 1, 0, TX, 0, 1, TY, 0, 0, 1, PBX, be y and 1. So this would be my GBA matrix converting from, let me write it there, sorry, AB, converting from B coordinates to A coordinates. If I want to get the opposite conversion from A coordinates to B coordinates, I need to invert the matrix. In this simple case where it's just translation, that just means flipping the sign on Tx and Ty, right? I said this before. Now, in general, if you have a affine transformation, it will have always this structure, or change of coordinates in affine space. So here will be the translation vector. Here will be 1, it will be all zeros. And this will be the linear part of the affine transformation. So this works in any dimension, any dimensional affine space. Okay. Great. So, and a few more things I need to clarify. One thing, I showed this slide last time, and I didn't explain one detail here, which I think is worth explaining. Do you see what is the catch in this? So this talks about rotations in 3D. It's in homogeneous coordinates. Doesn't really matter. That's just this one extra dangling row and column. But do you notice what is funny about these matrices? There is one inconsistency. Let's see if you can spot it. Exactly, there the signs are flipped on the y-axis. Do you know why is that? That's what I wanted to explain, because there is a good reason for it. That's because of the right-hand convention. So if we have rotations in 3D, as I said, we can be rotating about any axis, right? So if we have a basis in 3D, it could look something like this. And just like in 2D we have the default convention of counterclockwise rotation, in 3D the convention is the right-hand rule, right? If you put your thumb in the direction of the axis, then the rotation works like this. That basically curls along the fingers. There is a way to formalize this in mathematics, of course, but let's not go there. Let's just stick with the intuition. So that means that if I have a rotation about the x-axis, it works like this, right? It rotates the y-axis onto z and forms the loop, right? By the way, rotations in 3D have the property that they keep one axis constant and then just rotate in the plane orthogonal to that axis. So the reason why the rotation about y needs to flip is because if we are rotating about y, then the right hand convention dictates that z needs to rotate onto x, right? Which means that if I look at it from like a 2D perspective, if I have the x and z axis, that means that I actually have to do clockwise rotation. And that means that I have to flip the sign here. So I get my right hand rule in this case in the y rotation. In the z rotation, it's already satisfied, because if I'm rotating about z, the right hand rule tells me that x goes like this way onto y, so everything is cool there. I don't need to flip anything. Okay? And one more thing, I think you the one more thing I did not explain the last time is how this all relates to the perspective camera model. Because as we are already talking about homogeneous coordinates, it makes sense to cover this as well, because the cool thing about homogeneous coordinates is that they give you a very neat mathematical model for the pinhole camera and orthographic camera. So let's look at the perspective projection. So we are dealing with a 3D space, and we have some points in the scene, and we assume that the camera is located at the center of our coordinate frame. So this would be the z-axis, x-axis, and y-axis. And let's assume we have an image plane at z equal 1. Sorry, I previously had there minus. I changed it to plus because I don't think there's any good reason for the minus. I suppose maybe some conventions. So the idea is that we have these rays of light passing through the origin of this coordinate system, and they intersect the plane z equal 1 at some point u, v. Okay, so where do they intersect? That's quite easy to compute, right? So if my ray is defined by the origin by 0 and xc, yc, and zc, then to compute where does it intersect the z equal 1 plane, so those uv would be the coordinates of the intersection of the plane, and the plane has, of course, z equal 1. So from this you can see that tzc is 1, which means that t is 1 over zc. If I plug it in here, I see that u is xc divided by zc, and v is y, oops, that was supposed to be c, yc divided by zc. And that's what we have here. That's the, I guess, the simplest representation of perspective projection. It can get more complicated if you change the coordinate systems and so on. The tricky thing about perspective projection is that it's not a linear, not even affine transformation. It's really nonlinear. Nevertheless, it's very important in both computer vision and graphics. If you do some OpenGL, that's you definitely need to use the perspective projection to finally project things onto your screen. The cool thing is that while this perspective projection is not a linear transformation, it's not that far from linear. It's just one divide away from linear. And the cool thing is that we can almost represent the perspective projection using a homogeneous transformation. So this is how it works. If I write this matrix 1 0 0 0 0 1 0 0, and here comes the trig. Here I do 0 0 1 0 and 0 0 1 0. So notice if I apply to a nice homogeneous point with coordinates x, y, z, 1, what do I get? I will get x, y, z, and z, right? And this is just one nonlinear operation away from perspective projection. So what I need to do here is a z divide. I need to normalize this vector, divide the entire vector by z, 1 divided by z, and that will give me x over z, y over z, 1 and 1. Okay, and now this is a perfectly correct point. It's a point on the z equal 1 plane, so this is the point after the projection. So the perspective projection can be written using this 4x4 matrix and one z divide. So basically the entire nonlinearity concentrates at the z divide. That's also like how the graphics hardware works. I don't know, not sure if it's still the case, but it used to be like a big deal, this division by z, because division used to be expensive operation. I don't think that's the case anymore. Okay, so this was the perspective camera model. And a special case, I guess you could imagine if we were translating this focal point further and further away, we would eventually converge to orthographic camera, where orthographic camera basically assumes parallel rays. Okay? So orthographic camera, again, the coordinate system is the same. The projection plane is also z equals plus 1. But the rays I'm shooting through the plane are now all parallel. So in this case, actually, the orthographic projection, well, first of all, how does the orthographic projection look like? In this case, it's embarrassingly simple. The xc, yc, zc basically projects onto uv, which is just xc and yc, right? There's no math. The only thing we are discarding the zc component here. So this is a perfect linear transformation. which we can write like this. This matrix, all it does, it discards the last component. I guess if I wanted to put it in coordinates, if I could write it in 4D homogeneous coordinates, I would write, so this would be this is the perspective projection. And if I wanted to write orthographic 1, I could do this. 0, 1, 0, 0, and here, let's not get this wrong, like this. Let's see, what does it do? If I apply it to x, y, z, 1, it gives me, it's really no big deal, but it gives me x, y, 1, and 1, right? So this is exactly orthographic projection. So here I don't even need any set divide. Okay, so that's all I had to say today. Do you have any questions on this? And I think that's more than you needed to know for your first project. So I hope you will have fun coding it up. And we'll start with systems of linear equations next week, I believe. Chapter of the textbook? Don't remember, sorry. But I think it will be called systems of linear equations or something.
So I've done up to this point.
Let me stop the recording unless you want to be.